All right, today we're going to begin our study with geometry, and I'm going to take you first through a look at one of the most well-known formulas out there, the Pythagorean theorem. Just to kind of give you some insight, Pythagoras had his own school. They call it Pythagorean Brotherhood, and it's rumored that maybe he didn't even come up with the theorem. Not only was it kind of discovered simultaneously throughout the world, but it's thought that maybe his students came up with it, and then because they were studying under him, he got credited with it. But, there's no way to really prove or disprove who came up with it first. But this is the Pythagorean theorem in a nutshell. If you have a right triangle, and if we're talking about a right triangle, we mean a triangle with a right angle in it, then the two smaller sides, known as the legs, squared and added up, will give you the third side, the longest side, also known as the hypotenuse, squared. So whatever this side is squared plus this side squared equals the hypotenuse squared. Now, keep in mind those restrictions. It has to have a right angle in it, and it's always that longest side there that's by itself being squared. So let's take a look at some examples. The first one is we're trying to find the hypotenuse. And remember, the hypotenuse is always by itself. So I always tell students when I first teach them this to find that right angle and look at the side across from it. That's your hypotenuse every time. If you know it, you're going to write that number down squared. If you don't know it, like in this case, you write down the variable squared. And then the other two, doesn't matter the order you put them in here, just so long as it's being squared. And then from there, we're going to solve for x. So as we square 20, we're going to get 400. 21 squared is 441. Adding these two up, we get 841. And squaring both sides, we get 29 is equal to x. So this side right here is 29. Remember that hypotenuse should always be the longest side. So it should definitely be bigger than 20 and 21. The Pythagorean theorem can also work if you're not solving for the hypotenuse, if you're solving for one of the legs. So in this case, first identify where your hypotenuse is. And as you do this, I want you to notice that I didn't draw this as our typical right triangle like I did right here. Too many times students are presented with a right triangle that always looks like this or like this, where that right angle is always in the same corner. In fact, studies have shown with students learning geometry that sometimes they will call this a right triangle and this right here a left triangle, because they get confused thinking right triangle meaning, I don't know, this portion or this little box is on the right side of that line. So I want to encourage you, if you're going to be a teacher one day, to always try to present your problems in a different way, especially with shapes like this. So they don't always see right triangles like you see on those little cute math posters you hang up in your classroom, but they also see them turned around. And I thought when I first learned that, I was taking a grad school math class in geometry, modern geometry, and I was teaching geometry also. And so I said, you know what, that can't be true. So I was teaching an advanced geometry class with students that are pretty good at math. So I took out some cutouts of right triangles and I held them up in the air and I asked my class, I said, is this a right triangle? And I had several students, well actually everybody, say, yes, it's a right triangle. And then I flipped the right triangle from something like this to something like this and said, is this a right triangle? And I had a couple of students tell me no. And so I turned it back around to this orientation, and they were like, yeah, that's a right triangle. Flipped it around again back to an orientation like this, and they said, no, that's not a right triangle. So even with advanced students, sometimes they can be confused by what we mean when we say right triangle. So it's important that we don't always present these shapes in the same orientation, because as we flip them or spin them around, it still maintains its properties. It's still a right triangle. And this also gets them in the habit of looking at this and not assuming, because I guarantee some students will look at this and say, oh, that's the hypotenuse, and solve this by doing 8 squared plus 20 squared. So that's why I try to change it up with my students, and I want them, when they first learn this, to identify the right angle. Boom, there's your hypotenuse across from it. And so we know that goes by itself, and then that's going to equal x squared plus 8 squared. So this is 400. This is 64. And so I get x squared is equal to 336 when I subtract 64 from both sides. And now all that's left is to take the square root of 336. So the square root of 336, if you were to punch that in a calculator, is not a whole number. So we know that 336 is not a perfect square. So we're going to simplify this radical by factoring it. So I know, let's see, 3 will go into 336, and I get 112 there. 3 won't go into that because you add up the digits, you don't get a number divisible by 3. But I notice 4 will, because 4 will go into the last 2 digits here. So 4 will go into it. Let's see here, 4 times 25 is 100. 4 times 3 is 12, so 28 times. And 4 will go into 28 7 times. So I got a pair of 4s here. I'm going to take out that 4, and these are both prime. I'm going to multiply them back together, and I get 4 square roots of 21. So that's the length of that side. That's how I want you to write your answer in simplest radical form. It's about 18.3, but I want to see that you can do this measure right here. If you wanted to punch it in your calculator just to check and make sure it should not be bigger than 20, because if it's bigger than 20, then that should be the hypotenuse, and this should be the largest angle in the triangle. So it should be less than 20, the hypotenuse's value, which it is there. Now, there's lots of ways that you can prove this relationship will work if you have a right triangle, then a squared plus b squared equals c squared. In fact, there are many proofs out there that different people have published that are unique, that show that a squared plus b squared equals c squared. In fact, you can probably still contribute proofs to it if you can find one that's unique. I know I've heard that Abraham Lincoln even has a published proof of the Pythagorean theorem. But what I want to show you is a demonstration where you can do the Pythagorean theorem. And this is in your weekly resources. This is a demonstration I would like to do if I were in front of you in the classroom, where you actually cut it up yourself and you do this like you've got several pieces of paper here. You make a right triangle, and then whatever this side length A here is, you make a square with it. And then side length B, you make a square with it. And then side length C, you maybe trace out a square on a big piece of paper right here with the side length of C. So this represents A squared. It's an A by A square. This is a length B by B squared. So B by B is square there. So these two added up, the two squares added up, should equal the same area as C squared. And so this has been divided up into several sections that you can click on and drag to show this. Now sometimes you will have to move objects around to do that, or flip them over. Whoops, that doesn't flip it over. Let's flip it like this. There we go. Let me take a second just to get it all the way where I want it. I'll get there eventually. There we go. And so you can see how, oh look, it gave me a check mark. It shows you how you can cut that up, move it over, and that a squared plus b squared is c squared. You can also click over here in this corner, and it shows that you can choose different partitionings. So by that they mean like we can cut up these squares different ways to make them match over here. So that's just one way. There are many different ways that we can prove the Pythagorean theorem, but I think it's worth looking at to see you can't always do a visual proof like this in mathematics, so it's pretty cool. All right, back to our problems. Let's look and see what we've got. This question says a triangle has side lengths of 16, 48, and 50. Is the triangle a right triangle? So this is taking our thoughts on Pythagorean theorem and asking it a different way. So we've got some type of triangle here, and we'll assume that this right here is a right angle. And they tell us that our side lengths here are 16, 48, and 50. Now, when I'm talking geometry and they give me some shape and I start to sketch it out, for one, always sketch it out. Whenever you're doing a geometry or physics problem or any type of word problem, sketch it out. It makes things so much easier. But also, don't assume that we're doing this to scale. So for instance, one side's going to be 16, one side's going to be 48, and these look like they're almost the same length. So go by the numbers, not by how it's looking, because I'm a terrible artist here. So 16 is one side. That's the smallest side. The largest side is 50. So it's asking, is this a right triangle? If it is a right triangle, then 50 had better be the hypotenuse because it's the longest side. And so across from this, I don't know if this is a right angle or not. It's a question mark there. Across from that, I'm going to write down 50. And then the other two sides are 16 and 48. And it doesn't matter where I mark those. So if this is a right angle, then the Pythagorean theorem will work out here. 16 squared plus 48 squared will be equal to 50 squared. So this is 2,304. So this is 256. This is 2,500. So if these two add up to equal that, then we're in business here. But we get 2,560. Should be an equal sign right here, is equal to 2,500. This is not true. This is 60 more than this. So this is not a right angle. It's going to be larger than a right angle there. So we say no. Now if it were something like 6, 8, and 10, if that were the case, let's look at a problem like that. If we had a right triangle problem here, that was 6, 8, and 10, and we want to know, is this a right triangle? Then we could say, well, does the Pythagorean theorem work here? Does 8 squared plus 6 squared equal 10 squared? We get 64 plus 36 equals 100. So 100 equals 100. That is a true statement, so that would be a right angle then. So we could say yes there. This is helpful when you're doing something, a lot of times when I'm building something like my kitchen right here, it has cabinets. This is a floor plan looking down on it. It has cabinets right here. My dining room table is right here. I want to put in an island right here like this. And I want to make sure that this was parallel to the outside wall here. So what I did to do that was I took and nailed a little nail right there in the corner of the wall there, and going along the floor I pulled out a string, and with that string I measured off 4 feet, and then from this corner I went down 3 feet. Now I can move this string because it's just hooked onto the nail right there this way and swing the 4 feet in. Here, let me show you like this. If we make it a line like this, I could swing it in or out, and notice it changes the angle up here. And so I want it so that this angle is a 90-degree angle. That way I have a line so that this is a nice island coming in that's parallel to this wall and perpendicular to this one. So what I did was I had 4 feet right there. Let's go ahead and write that back in. Then I got a tape measure, and I made that tape measure come down like this from that 3 feet to the 4 feet. And I know that if this right here is a right angle, then that hypotenuse should be 3 squared plus 4 squared. It should equal 5 squared. Notice this gives me 9 plus 16 equals 25. So 25 equals 25. And so I had somebody hold the tape measure here, and I took and when I dragged it this way, the tape measure went out this way, and that would be longer than 5 feet, even though this was locked in at 4 and this at 3. If I dragged it too far in, whoops, let's spin that. If I drag it too far in like this, keeping it at 4 feet, then this would be less than 5 feet, maybe even less than 4 feet. But when I had my 4-foot string out like this, and then the tape measure equaled 5 feet right there, I knew that since this was 3 feet down, this must be a right angle. And then right along here, it was a string with chalk all over it. It's called a chalk line. I snapped the chalk line, and that made it so that I knew exactly where to build that island and nail it down to the floor. So it's used in construction a bunch. This is a common Pythagorean set of numbers here. We call them Pythagorean triples, a 3, 4, 5. And any multiple of that 3, 4, 5 works. Like in the last example, we'd use twice as much for each one of those, 6, 8, 10. So you could multiply them all by 10, 30, 40, 50. 30 squared plus 40 squared equals 50 squared. So that's one application you can use it for, is to verify that you do have a right angle. All right, try this one out. Actually, we already did one like this, didn't we? So this is going to be 6 squared plus 8 squared equals x squared. And so you get 36 plus 64 equals x squared. I almost gave the answer there. So 100 equals x squared, so x equals 10. That's our common Pythagorean triple there, 6, 8, 10. So moving away from the Pythagorean theorem, because hopefully many of you know that, and if you have any questions, you can use the homework there to ask me questions on that. Now, talking about similar triangles or similar figures in general are the same shape, but not necessarily the same size. So by same shape, we mean the angles are the same, corresponding angles are the same, and the corresponding sides are proportional. So before we actually look at this, let's look at, let's go back to that right triangle we just had a second ago, where we said we have a 3, 4, 5 triangle. And then we have a 6, 8, 10 triangle. So these two triangles are similar. And the reason why is this angle right here, let's call this ABC, and this one DEF. We can say that triangle ABC is similar, this little symbol means similar, to triangle DEF. And the reason why is their sides are proportional. Like if you take this side and put it over this side, you get 4 over 8. If you take this one and put it over this one, you get 5 over 10. And if you take this one and put it over this one, you get 3 over 6. Now what do these fractions reduce to? They all reduce to 1/2. Now what that also means is this angle, which corresponds to F down here, is the same. These two are congruent, whatever that angle measure is. And then angle B is congruent to angle E. And then lastly, A and D are congruent. So similar triangles have this, the corresponding angles are congruent, and the corresponding sides are proportional. So with corresponding angles, and I'm taking this, what you'd normally take maybe a week to a week and a half in a high school geometry class to learn, and I'm kind of breaking it down into just one short lesson here. But how can we know that all of those things are true about two triangles to say they are similar? There are some shortcuts. If we know that the three sides are proportional, like we just did here, we can say the two triangles are similar without even knowing what these angle measures are. So if you know the lengths of three sides and make these fractions and they work out, then you can say that they're similar. If you know two angles are congruent, so if I've got two triangles and you tell me that this is a 30-degree angle, this is a 60, and this is a 30 and a 60, then I can say these two triangles are similar. And so the sides, when I start matching up the sides, are going to have the same ratio between them. And then you can have side, angle, side. So side, angle, side is where, let's say we have two triangles again, and I know, say that this side is 10 and this one is 5, and then this side we'll say is 4 and this one is 2. And if you know that the angle is the same between them, let's say this is a 63-degree angle and so is this one. Notice that I don't know all three sides, and I can't use Pythagorean theorem because that's not a 90-degree angle. I don't know all three sides, I only know two of them. And I don't know both angles, I only know one of them. But it's the one that's between the sides I know. Then I can check and say, are the two angles the same? Yes, they are. Is the ratio between these two sides the same as the ratio over here? So 10 over 5 reduces to 2, and 4 over 2 reduces to 2. Yes, they are proportional. They have the same ratio there. Then I can say that these two triangles are going to be similar. So let's actually go back to that first problem we had. Are the two triangles similar? How do you know? So looking at this one, going back to our knowledge on triangles, we know that triangles have 180 degrees in them. When you add up all three angles, it should total 180. So on both these triangles, I know 2 angles, but not the third. Let's see if we can figure out what the third angle is. So for this triangle, I'm going to say 180 minus that 90 gives me 90 degrees, minus that 39 degree. Oh, not 36, 39 gives me 51. So this angle right here is 51. And so I can tell that I've got a 90 degree matching up with this 90 degree, and then I've got a 51 degree matching up with this 51 degree. So the answer is yes, these are similar by angle-angle similarity. Once you know 2 angles are congruent to 2 in another triangle, you can say the 2 triangles are similar. Let's look over at this one. So some things about the notation here. These 2 dashed lines and these 2 dashed lines mean that this side is congruent to this side. And this 1 dashed line and this 1 dashed line means that these two sides are congruent. Now within a triangle, if you have 2 sides that are congruent, then the angle across from those sides must be congruent. So these 2 are 68. And so once again, we can figure out what is this third angle here by saying what's 180 minus 2 68ths, minus both those angles. So this is going to give me 112, and then subtract another 68 from it, which gives me 44. So this angle is 44. Notice none of these angles right here match up with the 62. So I'm already done here. There's nothing else that I can show. I mean, it's showing that they're not similar. So this is no, because the corresponding angles are not congruent, the 2 triangles are not going to be similar. Let's try these out. It says, are the triangles similar? If so, write a similarity statement for the triangles and explain how you know the triangles are similar. So first, before we try to write the similarity statement, let's look at this first 2 right here that are set up. So I know that as far as corresponding sides go, the longest side corresponds to the longest side in the triangle. So I'm going to write 9 over 12. This is writing the triangle, parts of the triangle on the left over parts of the triangle on the right. You could really write it 12 over 9, but then it should be 8 over 6 next. But since I'm doing the triangles on the left over the triangle on the right, I'm going to put 6 over 8 and then 6 over 8 again. And if all these reduce to the same fraction, I know the 2 triangles are similar. So 3 goes into both of these, and you get 3/4. 2 goes into both of these, you get 3/4, 3/4. So this is a yes, they are similar by side, side, side. And so for our similarity statement, what they want in that is they want you to name the triangle. And there are several ways we can name this triangle. We can name it triangle ABC. We can name it triangle CBA. And you can name it triangle BAC. There's lots of ways you can name that first triangle. But if I'm writing the similarity statement here, the next triangle, the angles should match up. So what corresponds to angle A? In this case, since it's isosceles, either E or F, since E and F are congruent angles, would work. But I'm going to go ahead and just start with E. What corresponds to B? F does. And what corresponds to C? G does. Now C is across from the largest side, so it has to match up with G every time there. So that's one way you can write that similarity statement. If you name the first triangle CBA, then C corresponds to G. So G has to be listed first. And then we've got FE. So that works there. And then lastly, if you would have named it BAC, then you could have written it out as triangle FEG like this. But notice, because E and F are the same measure as A and B, it doesn't matter really the order you write those, but the G has to match up with the C in this case. And there's more ways you could write that combination of B, A, and C, but that's how we're going to leave it there. So for the next one, we've got a triangle inside of a triangle. So if it helps you, you can redraw that small triangle, 6, 8, that's a right angle, and then you've got ALW. And then so I'm going to rewrite, I'm just going to kind of scratch out all of this. This whole length of AE here is 12, and this whole length of AC here is 16. And then I'm just going to kind of ignore that line in the middle there. So I'm looking at this triangle right here and comparing it to this one. Don't forget, though, that this is a right angle. That's an important piece of information. So they both share that right angle. So we know that We don't know the third side. We could figure it out using the Pythagorean theorem, but I think it's easier to see if side angle side will work here. So for side angle side to work, I'm going to put 12 over 6, and then 16 over 8, and see if they reduce to the same fraction. So 12 over 6 reduces to just 2, or 2 over 1, and 16 over 8 reduces to 2. So this side right here is similar to this one, and this one's similar to this one right here, not congruent, but similar. And then their sandwiched angle there, the angle in between those sides, are congruent. So, because they're both right angles. So this is similar by side angle side. So this is another yes, similar by side angle side. And writing out the congruency statement, we can say that triangle, I'm going to start with the small one here, AWL, is similar to triangle. I went from A to W, so let's go A to E now. AEC. If you wrote it differently, you could have said triangle, let's start with the little one again, LAW, LAW, but then you would have had to have said triangle CAE here. So once again, lots of different ways we can write it. The first one doesn't matter the order, so long as the second one, the angles match up. Now, as far as similar triangles go, I'm not going to really go in depth in this course about isosceles triangles or even really making you write out these similarity statements. What I want is applications of similar triangles. And the reason why I'm going through it is because one huge application of similar triangles is trigonometry. And so we'll see that in the next lesson when we go over to trigonometry. It's kind of the basis of why right triangle trig works, is all based on similar triangles. But for today, we're going to look at a few applications that are dealing with word problems. And you may have remembered these from your high school course, you may not. But everybody loves word problems, right? So let's take a look at a few of them. It says a tree casts a shadow that is 12 feet long. So remember, when we're dealing with a word problem, sketch out the problem. So we've got a tree. Let's draw the ground. So here's our tree. And here's Brad. And I'll just draw the shadow like this. And here's Brad's shadow. Like I said, you don't have to get real complicated with these. Let's see, up here's the sun. Right there. There's our sun shining. And so the tree is 24 feet tall. The shadow of the tree is 12 feet. Brad is 6 feet tall, and we want to know what is his shadow's length. So you say there's no triangle here, but remember that the sun rays are coming down from the sun like this, and that's what's making the shadow happen. Because the tree is blocking the sun rays, and it's shiny everywhere else but where that shadow is. Then once again, it's because Brad is pretty close to this tree, the angle to the sun is about the same. So we're going to assume that both are standing straight up, so they're right angles there, and that they're so close to each other on Earth that this angle right here is the same. And so now I can say that the two triangles are similar. Why? Because of angle-angle. They've got two angles that are congruent. And so with that being the case, we know that this side and this side have a ratio that's the same as this one and this one. So I'm just going to put the tree, parts of the tree, over parts of Brad. Or you can say the triangle on the left over the right. I usually do something like this just to remind myself that I'm writing parts of the tree up top. So 24 right there, it corresponds to 6. 12 right here, it corresponds to x. Now, I know that these two fractions are equal. And so there's a couple ways you could solve this. You could just say, hey, 24 divided by 2 is 12, so divide this by 2 also. But it's not always that straightforward. So the trick that works every time is that one we learn that's called cross multiplication. So you say 24 times x, and write that down, and 12 times 6, and write that down, and then divide, or these, keep your equal sign there, divide both sides by 24, and you'll get 3 is equal to x. So his shadow is 3 feet long here. That's what x equals. So that's all you got to do. Set up your triangles, draw a picture. Notice how much easier that makes it, drawing a picture. I want to see that in your work, your picture's drawn there. Try this one. A 40-foot flagpole casts a 25-foot shadow. Find the shadow cast by nearby 200-foot tall building. So here's my building and my flagpole. We've got a shadow coming down like that from the flagpole, the same. And so we know the flagpole is 40 feet tall and it's got a 25-foot shadow. The building is 200 feet tall. It wants to know the length of the shadow right here. Once again, the two triangles are similar because these two things are standing straight up. This angle is the same if we're assuming the sun's somewhere up here. And so I'm going to put parts of the building over parts of the flag. The building is 200 feet tall. The flag is 40 feet tall. The building, we don't know how long the shadow is. The flag has a 25-foot shadow. And then I'm going to cross multiply. X times 40 is 40x. 200 times 25 is 5,000. Divide both sides by 40 and you get 125. So x equals 125 feet. We're not always finding the lengths of shadows, though. I think it's more useful to find the height of things, especially like if I got a tree I'm cutting down in my front yard and it's really tall and I'm worried about hitting a house. I can get a good estimate on how tall that tree is by using my shadow and the tree shadow to get an estimate on it. But anyway, a tower cast a 7 meters long shadow. Can't read today. A vertical stick cast a 0.6 meters long. It tells me the height of the stick. How high is the tower? So let's say, let's draw our picture. So here's the tower, and it's casting a shadow that is 7 meters. And then we've got a vertical stick with a 0.6 meter, 0.6 meter. The stick is 1.2 meters high. We want to know how tall the tower is. Once again, this is all shadow casting, so we're talking about the sun. This angle equals this angle. These are both right angles, so the two triangles are similar, so we can do this method. So I'm going to put the tower over the stick here. So we've got an x. It corresponds to the height here of 1.2, and that equals the shadow length of the tower is 7 over the shadow length right here of 0.6. Cross multiply and solve. So this should give me, I think, 8.4 is equal to 0.6 times x. Divide both sides by 0.6, and so I get 14 is equal to x. All right, and that pretty much sums up everything that we're doing today. We're going to try out some of those Pythagorean theorem problems for homework tonight and a few similar triangle problems. I really, a couple of these word problems is all I really expect of you. You'll see it on your homework. I really just want you to be refreshed on what similar triangles are so that when we talk about trigonometry, we've got a little bit of a base to build off of. Okay? Let me know if you have any questions, and thank you for working hard in the class.